friends, welcome to lecture 3.6, which is the final lecture or the module in the third unit on the review of Fourier transforms. This particular module is going to be presenting a review of the discrete Fourier transform and also the concept of periodogram towards the end. So, this is a very practically relevant transform, because this is the transform that we apply to sample data. Until now we have studied all the theoretical transforms, but now we are going to ask certain questions that are relevant to us in practice. So, the objectives of this module is to review and learn the concepts of discrete Fourier transform and conclude that with a periodogram. Now, the motivation for looking at discrete Fourier transform, as I have explained to you, is to consider the practical scenario where first of all the signals encountered in reality are not necessarily periodic. More importantly, the signals that I have for analysis are finite length. I cannot conduct an experiment for infinitely in time. So, how do I deal with the finite length data? Because if you look at all the 4 theoretical variants of transform or even the discrete time Fourier transforms that we have learned, they assume that the signal is either periodic, which may not be the case in practice, or if the signal is aperiodic, it assumes that it exists forever or that you have the knowledge of the signal over infinite time. Neither of this is true. So, now how are we going to deal with this? And there is a second issue with the use of discrete time Fourier transform. Even if I am given, let us say, the signal for a very long period of time, as far as computing the DTFT in practice is concerned, I can only compute it over a grid of frequencies or at a discrete set of frequencies. It is obviously not possible to compute the DTFT over a continuum. So, can I compute the finite length discrete time Fourier transform, that is restrict the summation to the extent that I have? Can I do that? If I do that, what is the consequence? Or I do not, I would still like to use the discrete time Fourier transform as is, but by first constructing artificially the infinitely long signal from the finite length data. Is that another possibility? And if I do that, what kind of extensions are possible outside the observation interval, and what does a particular extension of the signal lead to, and so on. So, the message is I need to handle finite length data, and I need to compute, I can only compute DTFT at discrete set of points. So, some form of discretization of the frequency axis, in other words sampling in frequency, is therefore inevitable. With these remarks, we introduce the discrete Fourier transform, and we ask what is the consequence of computing this discrete Fourier transform with respect to the theoretical discrete time Fourier transform. So, when I restrict the DTFT, so I will say, well, I will ignore what has happened outside the interval of my observation, and I am going to only compute the transform for the length of data that is available to me, and as I mentioned earlier, I am going to compute it at specific frequencies. So, now the subscript n returns to the forum. Earlier in the discrete time Fourier transform, the frequency axis is continuous. Now, because I am going to compute it over a grid like in any other software like numerical integration and so on, now I have f subscript n. This n keeps track of the grid point at which I am evaluating the Fourier transform. So, this is not much different from the discrete time Fourier transform. It is taking birth from DTFT by restricting it to the interval of observation and evaluating it on the grid. So, the expression is more or less the same. I replace f with f subscript n, and I restrict the summation limits of summation to lower limit to 0 and upper limit to n minus 1. That is a convention that we follow. You have to be careful. In software packages, the starting index is n equals 1. So, you have to adjust the code for the computation of DFT accordingly. Now, here n is the length of the signal. The reason for calling this as discrete Fourier transform is because now you are not only dealing with sample data that is in time, but also you have sampled the frequency. So, it is no longer just discrete time Fourier transform, it is discrete time, discrete frequency Fourier transform. Now, that is a mouthful. So, therefore, we simply call it as discrete Fourier transform, understanding that it is discrete in both time and frequency. That is the reason for this name. Now, the big question that we have is what should be the grid spacing? That is, how fine should be the grid? Should the grid be uniform, non-uniform? If it is uniform, then what is the spacing that I should choose? What is the consideration and so on? Now, interestingly, there is a parallel question, there is a similar question that arises in sampling of continuous time, sampling continuous time signals, which we had discussed earlier in the context of sampling and sampling theorem and so on. There we asked a question, how fast should I sample, whether I should sample uniformly, and if I sample uniformly, what should be the spacing between two sampling instances. It is exactly, although it is now we are dealing with frequency, the questions are very similar. There in time, sampling in time, our consideration was that I should not lose information. What I mean by this is, if necessary, I should be able to reconstruct the continuous time signal from its sampled version. We can place a similar requirement here, and we can say that I would like to choose the grid spacing, assume that we are going to deal with uniform grid. I am going to choose a grid spacing such that I will be able to recover the continuous function, the continuous Fourier transform, which is x of f that I would have computed otherwise, from the sampled version of x of f. That is, I would like to recover x of f from x of f subscript n, and it turns out that you can do this if and only if you choose the interval in frequency as 1 over n subscript l. N subscript l is now the length of the signal that you have, all right. So, if I have a signal of length n subscript l, then x of f, that is the discrete the continuous function, is perfectly recoverable from its sampled version if and only if the frequency axis is sampled uniformly at with this spacing, all right. Of course, we are only going to sample in the fundamental frequency range. That situation does not change because we are still dealing with discrete time signals. So, in terms of the cyclic frequency, the spacing, grid spacing is 1 over n. In terms of the angular spacing, its angular frequency, the spacing is 2 pi over n subscript l. Now, you can see you can refer to this book by Provakis and Manolakis for proof, but there are other books as well that will give you proofs of this statement. That is, they will prove to you that you can recover x of f from x of f n. Now, with this result, having accepted this result, now we can talk about the DFT a bit more in detail and also study the consequences of restricting the summation to the observation interval. Now, formally we say x of f n is x of n, the same notation that we used for discrete time signals. In discrete time, in time we use k to keep track of the sampling instant, in frequency we use n to keep track of the frequency point. So, x of n is nothing but what you have seen earlier, and we evaluate n from that is, we evaluate the DFT for all values of n running from 0 to n minus 1, and given at the bottom in 3b you have the synthesis equation, all right. So, this is a reversal of what we have done until now. We had presented the analysis equation first and then the synthesis equation. Now, we are presenting the synthesis equation first because now we are really concerned with the practical situation. The analysis equation, synthesis equation allows me to recover the signal whenever I want. Notice again the difference of 1 over n as a factor in front of the summation. In the synthesis equation I have a 1 over n, whereas in the analysis equation I do not, but the forms of the summation look the same, except that in the analysis I am summing over time and in synthesis I am summing over frequencies. Now, again the similarity of this allows me to write simplifies the coding problem. I just need to write one algorithm and change the sign here. Now, in fact, it is further simplified if you consider what is known as a unitary DFT, where I deliberately introduce this factor of 1 over root n in my analysis equation, so that the synthesis equation also has 1 over root n. This is called a unitary DFT, and the reason is that it preserves the square 2 norm of the signals. In other words, if I take the square 2 norm of the signal that I have observed, that is the same as the square 2 norm of the DFT that I have computed, and that is why it is called a unitary transform and so on. Notice again, this is very important, until it becomes a practice you should keep telling yourself that you are computing at frequencies n over big N, where n runs from 0 to big N minus 1, and big N is the length of the signal. Of course, we have dropped the subscript L here. This is called an n point DFT, because I am evaluating the DFT at n points on the frequency axis. So, now just to obtain an insight of how DFT is working, or if I want to know how x of f can be recovered from its sampled version, that is a continuous Fourier transform, not continuous time Fourier transform, the continuous function Fourier transform from its sampled version. How do I do it? Well, this is the expression that allows you to recover x of f from its sampled version. I am avoiding the derivation here, but you can refer to any standard signal processing text like such as Provakis and Manolakis to see how this expression recovers the x of f for you. Now, it turns out that there is a strong similarity of this expression with that of recovering x of t from its sample data, which we have not seen in this course, but again any standard signal processing text will give you the expression for recovering x of t, the continuous time signal, from its sample version. So, the reason for pointing out the similarities is, again, there are a lot of similarities and dualities between time and frequency domains. So, now the other condition that is required, one more point of similarity is that the number of points that you choose on the frequency axis or frequency grid should be greater than or equal to the number of observations that you have. That means you should at least have as many points on your frequency axis, assuming uniform spacing, as the number of observations that you have, which means I am allowed to evaluate at finer points, but then what is the consequence of doing that we will discuss shortly. First, let us understand what is the consequence of sampling the frequency axis. Early on in this lecture we said, is there a possibility that I can construct an artificial infinitely long version corresponding to the finite length signal that I have observed by some extension. What we mean by extension is, for example, you could assume x of k, the original infinitely long signal, to be, let us say 0 outside the interval of observation. So, I can say that that is one possibility, or the other possibility is that I assume a periodic extension of the finite length signal, and so there are several possibilities. I can assume that the signal was constant before and after I observed, and so on. So, now we are asking, when I compute the DFT and when I am sampling the frequency axis. So, in DFT I am doing two things, I am restricting the summation limits to the observation interval, and I am also sampling the frequency axis. So, what is the consequence of sampling the frequency axis? That is what we are studying here. So, I am just showing you the derivation here, I am not really going to go into the details, but as a simple exercise for you, go through these derivations here. These are again found in standard text. So, we start with the expression for the DFT coefficient, the discrete time Fourier transform at that point n, and then ask what this means. Then you can re-express this summation, you can rewrite the summation as a double summation. We have deliberately introduced that, so a double summation there, and one more change of variable will bring this third expression for us in equation 6. Now, we introduce a new signal x subscript p, which is this infinitely summed up xk minus ln, and there is a reason for doing that. Here you can see that this particular signal xp subscript k is periodic, it is actually periodic with a period n. That means you can show clearly that xp of k plus n is nothing but xp of k itself, and that is why we have used a subscript p to indicate that this infinite sum is nothing but a periodic signal. Plugging in this new variable into equation 6 gives me equation 7, well not exactly, but the right hand side of equation 7, where I have sigma k equals 0 n minus 1 xp of k e to the j minus 2 pi k over n. Why are we paying attention to this expression? That is because this has very strong similarity to what the expression that I had in the discrete time Fourier series. For a when I am looking at periodic signals, remember I would use discrete time Fourier series. When I am computing the coefficients of discrete time Fourier series, I use Cn. So, what I am showing you here for your comparison, replace this infinite summation, inner summation in equation 6 with xpk, and then compare with the expression that we have for n times Cn that you had for in a discrete time Fourier series expansion of xp. Then you will see that DFT has very strong similarity with discrete time Fourier series. The only difference is I am computing n Cn instead of C subscript n. In other words, the discrete Fourier transform coefficient is nothing but NCn itself. So, that is the point, right. It is x of n is NCn. What is the consequence of what is the point in actually comparing these two? The main point is in restricting the summation to the observation interval and sampling the frequency uniformly with a frequency spacing 1 over n amounts to assuming that the infinitely long signal which I have not observed is periodic with the period equaling the length the duration of the observation. Okay. So, that is regardless of the nature of the underlying signal, which means implicitly when you compute DFT you are assuming that the underlying infinitely long signal is periodic. That is a major assumption that you are making, and many of us probably even do not take note of this when I compute the Fourier transform in practice in all the software packages. When I am using FFT, which is an algorithm to compute DFT, implicitly I am assuming that the infinitely long signal that I have not observed is actually periodic with the period equaling the length of the observation. Okay. So, that is a very important assumption remark and observation that we will use later on. So, x of n is nothing but NCn. What is this Cn? Cn is the coefficient of the discrete time Fourier series for the signal that you observed. So, I take the signal that I have observed, I compute DFT, that is x of n. My friend takes the same signal and assumes that it is a periodic signal and that he or she has observed the one full period of this periodic signal and computes the Fourier series coefficients. When I take the Fourier series coefficients and multiply with n, it will exactly match the DFT coefficient that I have computed, that is the point, all right. So, this is something that should be kept in mind and should be reinforced within in our minds until we are very clear about it and we know it for sure. So, moving on, just as a passing remark, the DFT inherits all the properties of the discrete time Fourier transform, with the only difference that we replace convolutions with circular convolutions, because remember DFT involves finite summation, whereas discrete time Fourier transform involves infinite summation. So, to summarize, this is the expression, these are the expressions for the analysis and synthesis associated with DFT. Also the synthesis is also known as inverse DFT. You have to be careful, in many software packages the 1 over n may not be there or may be there and so on. When you are computing the inverse DFT, you should check the documentation of that particular software and then manually incorporate this 1 over n factor, because normally in any software package you will have the routine FFT to compute the DFT in a computationally efficient manner, and the inverse FFT will simply implement the same thing, that is with xk replaced by the Fourier coefficients and e to the minus j replaced with e to the j. So, the inverse Fourier transform may typically only give you this summation omitting this 1 over n factor, you should manually accommodate that. Now, this 0 padding something that that is something that I mentioned here, we will talk about it a bit later. You can also rewrite this DFT equations by introducing a new quantity W subscript n, so that it becomes easy for shorthand calculations. But in practice, we use what is known as the fast Fourier transform, and I will talk about it shortly as well. So, there are certain useful points to remember when you are using DFT. First of all, the frequency resolution in cyclic frequency is 1 over n, angular frequency 2 pi over n, and many a times you see these recommendations and suggestions of padding with zeros. What we mean by padding with zeros is, if I have 98 or 100 observations, then the software may pad another 100 zeros to your data and make you believe that now you have 200 observations. Whereas you had 100 observations, now padding with 100 zeros brings it up to 200, and you compute the DFT of this, you feel that you have much better resolution, because 1 over 200 is smaller than 1 over 100. So, you feel that you have computed DFT over a finer grid. Unfortunately, padding with zeros does not provide any new information. That means, you will not get any finer information or finer resolution and so on. All it does is it can improve the display. In fact, the other point associated with padding with zeros is, let us say I have 100 observations, I compute the DFT. So, I have computed DFT at 100 frequency points. I would like to know the value of the DFT at in between these 2 frequency points that I have computed. So, I need some interpolation. Padding with zeros is one form of interpolating the DFT between 2 points that you have computed. So, it is one form of interpolation. You can actually have many other ways of interpolation. So, what padding zero padding does is, it gives you a better display of the spectrum, that is all. It does not provide any new information. In fact, sometimes padding with zeros is not recommended, because zero padding at the front and the end of the signal can introduce artificial discontinuities, which is also not recommended. So, there are a few articles on the web that you can search for where they critically study the zero padding business. Okay. So, again, to reiterate, DFT is calculated assuming that the infinitely long signal that I have not observed is periodic with the same period as same as the length of the observation. So, what you are actually computing is not Fourier transform, you are actually computing Fourier series coefficients, you should remember that. And in an n point DFT, only n by 2 plus 1 frequencies are unique. For example, if I have a 1024 point DFT, then only 513 frequencies are sufficient because of the conjugate symmetry and so on. So, this is simply the property due to the property of the Fourier transform. And the basis blocks are still cosines and sines, cosine 2 pi k over n and sine 2 pi k over n, and the quantity n, the small n, denotes the number of cycles completed by each basis block in the duration of your observation of your data record, all right. And the value at n equals 0 always corresponds to the DC component. We have mentioned this earlier also. So, in practice, as I said, DFT uses an algorithm called fast Fourier transform, which was developed by Cooley and Tukey in 1960s. It is a computationally efficient algorithm. Prior to that, it was quite difficult, or in sense of computational burden, to compute the DFT. The moment this FFT algorithm came about, it revolutionized the world of spectral analysis. Now, fast Fourier transform is not a new transform, it is essentially a simple an algorithm for computing DFT, whereas DFT is indeed a different transform from DTFT. What did the FFT do? It essentially it reduced the number of operations from n square. If you look at the summation in DFT, and if you have to compute over n frequency points, then the number of operations required is n square. FFT reduce that to n log n. Log n here, logarithm is to base 2. Okay. Now, that is a considerable reduction, otherwise you would require huge computers to or supercomputing to compute the Fourier transform. And although for a long time FFT algorithms were fast when n was exactly power of 2, that was also another reason why 0 padding would be done. If I have, I cannot always collect observations which are power of 2. I would, if I have 100 points, I would add 28 zeros to bring it up to the next power of 2, which is not such a requirement now with modern algorithms. They can work without even 0 padding. So, the MATLAB routine that is used to compute the Fourier fast Fourier transform is FFT itself, and so is the case with many other packages as well. But you should read up the documentation on FFT. Now, finally, having computed the FFT, I would like to compute the power spectrum or power spectral density and so on. So, the question is now amidst all of this that we have learned, which is that computing DFT amounts to assuming the underlying infinitely long signal to be periodic and so on. Am I actually going to compute power spectral density, energy spectral density, or what is it that I am going to compute? Because of the fact that DFT, computing DFT implicitly amounts to assuming the infinitely long signal to be periodic, essentially I can only talk of power spectrum, I cannot really talk of any density strictly speaking. So, when I take the squared magnitude of the DFT coefficients, I will only get power spectrum, but not necessarily densities, because implicitly I am assuming the underlying signal to be periodic, and we know for periodic signals densities do not exist. So, what do we do now? How come people talk about densities and so on? Well, the densities that are talked about in practice are actually heuristic, and this is known as periodogram, which was introduced by Schuster as early as 1897, even before decades before FFT was invented. So, the power spectrum of the finite length signal, now again because I am assuming that the underlying signal is periodic, I can only talk of power spectrum. The power spectrum for a periodic signal, as we have seen earlier in lecture 3.3, is mod Cn square, and we know from the relation between the DFT and the Fourier series coefficients, mod Cn square can be written as mod x of n square by n square, because x of n is n times Cn, remember. So, mod x of n square is nothing but the squared magnitude of your DFT coefficients. Your DFT coefficients are going to be complex. So, a heuristic power spectral density known as a periodogram can be introduced, which is denoted by this different kind of font P. Apologize for the confusion between the P for the power spectrum and this P for the periodogram. So, we will say this as P double P just to distinguish. So, this double P of f of n is nothing but a heuristic power spectral density. It is the power over delta f. Ideally, you cannot define density that way, but density has the units of power per unit frequency, and therefore, we are dividing power by delta f, and that is nothing but n Cn square, because delta f is 1 over n. Remember, in DFT delta f is 1 over n. Therefore, I have now mod x of n square over n as being the heuristic power spectral density, which is called the periodogram. And this is in terms of cyclic frequency. If I look at angular frequency, I have to divide, I have to include an additional factor of 2 pi, because then I will have to divide this by delta omega instead of delta f. That is the reason I have a 2 pi here. Now, the MATLAB command routine that computes a periodogram for you is periodogram itself. You have to be careful, you should know whether by default it returns the periodogram in terms of angular frequency or cyclic frequency. It turns out that the default is angular frequency. So, it is a 1 over 2 pi that is involved. There is yet another aspect of periodogram which I will demonstrate to you, at least I will talk about it in the MATLAB session that will follow this module. So, with this we come to a close of this module and this unit itself. In this module we have talked about discrete Fourier transform, which is practically the most relevant one. Therefore, you should spend some time understanding it, and presented the concept of periodogram. It's a very subtle concept there, that we are not really computing any densities per se. Theoretically, it is a heuristic spectral density that we are computing. There is a reason for introducing the spectral density, because we would like to know what is the power per unit frequency, and more importantly when we move to the world of random signals, which we do not in this course, then we can only talk of spectral densities, and I would like to have an estimator of spectral density and so on. So, there again the periodogram comes handy, although it is not a great estimator of the spectral density of random signals. So, these are some of the references for your perusal. Please read through the relevant sections of these books, and the paper by Custer is interesting. Now, Fourier transforms, as I said, have enormous set of applications. So, you should really pick, go and do a quick literature review, select any paper on Fourier transform, application of Fourier transform which is relevant to your field or something that you are familiar with, and study how Fourier transforms have been applied. In fact, there are papers which talk about how our brain implements Fourier transforms very efficiently, and particularly there is an article in SIAM which talks about how the ear implements Fourier transforms and filtering, where it is able to recognize many sounds of simultaneously which are of different frequencies without any ambiguity. Okay, so with that note we will close this module, and please go through the video lecture of the MATLAB session that follows this module. Thank you.